Hello again everybody. Today we're going to talk about the tight binding method, which provides us with a complementary perspective with respect to the nearly free electron model that we discussed in the last lecture. In the nearly free electron model, we start with an electron uh, in a zero periodic potential, and then we turn the periodic potential on gently. Right, and in the tight binding method, which we are going to refer to as TB for tight binding, we start with a overwhelmingly large periodic potential, and we allow our electrons to gradually unbind and become Bloch electrons. So we're going to start from the opposite end of the spectrum with respect to the free electron picture, and interestingly, we'll arrive at the same sort of result. There is a little catch though. The two approaches, the nearly free electron and the tight binding approaches, will converge to the same sort of results in the end as long as we have sufficient number of terms, which are also called as basis functions, in the series representation of the wave function. What do we mean by that? In order to understand what I just said, we'll have to go back and recall what we wrote down as our wave function for our nearly free electron system, and then after that we are going to write down the form of the wave function as prescribed within the tight binding model, and we will understand what we mean by sufficient number of terms. So here is our expression for the wave function under the assumption that our electron is inhabiting a periodic potential, and under those circumstances our wave function is going to be given by the Bloch's theorem, which basically means that our wave function is going to be a product of a plane wave part, a phase factor e to the I k dot r, and a periodic part uk of r. So if our uk of r is a periodic function, it can be expanded as a Fourier series, where the g's are of course our reciprocal lattice vectors, and the ugk quantities, which are over here, those are our Fourier coefficients, right? And these quantities over here, e to the I g dot r, these are what we call as our basis functions. They are plane waves, but in this particular case they are also our basis functions. And the point is that if the number of our basis functions is very large, meaning we have a lot of terms in this Fourier series, then we are essentially representing our wave function very accurately. Now let's see what the situation is with the tight binding picture. So within the tight binding method, we write our wave function as a linear combination of some other functions phi, right? So we have phi over here, and we have c nu, which are the coefficients. So we are writing our wave function as a linear combination of some auxiliary functions phi. Now, what are phi? So things begin to get a little complicated now. So these were our auxiliary functions. These were the functions using which we wrote down our wave function. And these phi functions are basically written as a linear combination of small phi's. And by the way, these small phi's are nothing but our atomic orbitals. They could be the 1s, 2s, 2p, etc. Atomic orbitals. So let's say we have a periodic arrangement of atoms, and each atom is going to come with it the atomic orbitals 1s, 2s, 2p, 3s, and so forth. So what we are saying is that we can create our capital phi function as a linear combination, a special type of a linear combination of our atomic orbitals, which we are representing as the small phi. And Rj are the locations of our atoms. Okay, so here are our definitions, right? The small phi are the atomic orbitals, or AOs. New labels are atomic orbitals. They could be 1s, 2s, 2p, etc. And Rj are the atom positions. They could also be, they are actually the unit cell positions, but if you have just one atom per unit cell, let us say, then those become the atom positions. And our capital N is actually the total number of unit cells, where n is of course a very large number, right? So 1 over square root of n is something like a normalization constant, and n is basically the number of unit cells in our system. So our capital phi over here is nothing but a linear combination of atomic orbitals. It is a interesting kind of a linear combination of atomic orbitals, because you got your atomic orbitals there, but it has something like a phase factor multiplied and summed over all of the atoms of the system, all the unit cells of the system, right? But still, phi is a linear combination of atomic orbitals. And for that reason, it is called LCAO, which stands for Linear Combination of Atomic Orbitals. Okay, here is the interesting part. The LCAO that we have defined, the linear combination of atomic orbitals that we have defined here, satisfies Bloch's theorem, right? In fact, it is constructed so that it satisfies Bloch's theorem, meaning this quantity over here, the linear combination of atomic orbitals, satisfies Bloch's theorem. This entire piece here satisfies Bloch's theorem, and so by construction, our wave function here satisfies Bloch's theorem, right? Now what we are going to do is we are going to try to see how this phi function satisfies Bloch's theorem. Before we prove that phi satisfies Bloch's theorem, we are going to make one simplifying assumption and make one interesting, important observation. The first simplifying, the simplifying assumption that we are going to make is that we are going to just say that our nu can take on only one possible value, the 1s level. So we are going to just allow nu to be just 1s instead of 1s, 2s, 2p, and so forth, right? So which means we'll be able to safely get rid of this this summation. Note that this is sum over all atomic orbitals, right, by construction. So by saying that nu can take on only one value, the 1s value, we are just saying that okay, we can get rid of this particular summation. Okay, so we have just conveniently dropped the new superscript over there, and since there is only one term within the summation, we can just get rid of that CV, C nu, and so our wave function psi excuse me, psi k is equal to phi k. And now for the interesting important observation, and this has to do with Bloch's theorem itself. What we're going to do is very simply state an alternative form of Bloch's theorem. So there it is. This is an alternative statement of Bloch's theorem. First of all, what I've written over here is just our Bloch's theorem itself. This we are familiar with based on the previous lecture. If our electron is traveling, residing, inhabiting a periodic potential, then our wave function psi k of r is written as a product of e to the I k dot r times the periodic function u k of r. So that's the familiar Bloch's theorem. Now what we are saying is that okay, let's consider this wave function psi k of r plus capital R, where capital R is a lattice vector, right? That's a lattice vector that translates any lattice point to any other lattice point, right? So if we consider the wave function psi k of r plus r, small r plus capital R, then all we need to do is go back to this function over here and replace small r with small r plus capital R. That's exactly what we have done over here. Going from here to the next step, right? We have just expanded the exponential. E to the I k dot r plus r is written as e to the I k dot capital R times e to the I k dot small r, and remember that uk of r is a periodic function, and so uk of r plus capital R is the same as uk of r. Okay, now e to the I k dot r times uk of r is nothing but our wave function itself from this equation over here, and so our final result is psi k of r plus capital R is equal to e to the I k dot capital R times psi k of R, where remember of course that capital R is a lattice vector in real space. Okay, so this is an alternative statement of Bloch's theorem, and as long as we are able to prove this relationship, that this quantity here is equal to this, we have essentially proved Bloch's theorem. So if we, going back to what we were talking about, our LCAO, linear combination of atomic orbital phi, which we are using to represent our wave function within the tight binding approximation, we want to go back to this quantity over here and prove that this indeed satisfies Bloch's theorem. Or alternatively, really what we are trying to do is show that psi k of R as prescribed within the tight binding method satisfies Bloch's theorem. That's essentially what we are going to do next. So let me give myself a little room. Okay, so we start our proof by considering psi k of R plus R1. Capital R1 is any particular real space lattice vector, and we are going to write down the expression corresponding to this quantity. And here is our expression, and we can actually go back and remind ourselves that psi k of R equals phi k of R, which is what you see at the top of the screen. And if you go back a little bit further, we realize that our phi k of R is equal to 1 over square root of n times that particular summation over there, where small phi on the right side is nothing but our atomic orbital, in this particular case the 1s orbital, right? So that is our phi k, and so we go back over here and we have written down the first line of our proof. And in the first line of our proof, we have chosen a specific real space lattice vector R1, because remember we are attempting to prove the new version of Bloch's theorem that we just wrote down, right? So we are considering a special real space lattice vector R1, and we are asking the question as to what our psi of R plus R1 would be. And so we take the expression for psi of R and replace the small r with small r plus R1, and we get this expression over here. Right? So R has been replaced by R plus R1. That's it. Okay, so let's plug along. Okay, so there is our second step. All we have done is a little mathematical trick. We want our exponential over here to look like this quantity over there, and to make that happen we have simply multiplied and divided this entire expression by e to the I k dot r1. So that's the multiplied factor, e to the I k dot r1, and there is the corresponding factor dividing the entire thing that goes into our exponential over here and becomes rj minus r1. And of course we have grouped, we have just taken that and regrouped things and written it in this manner. And so you see you have rj minus r1 up here in the exponential, and you have rj minus r1 over there. So it's just a little neat mathematical manipulation. Why did we do that? The reason we did that is simply because now we can write down 1 over square root of n times this entire summation as psi k of R. That's exactly what it is. And why does that work out? It is because if Rj is a real space lattice vector, so is Rj minus R1, because R1 is also a real space lattice vector. Remember that you have a summation over j, and which means that you are summing over all real space lattice vectors Rj, and it does not really matter whether you are summing over Rj or Rj minus R1, because R1 is also a real space lattice vector. And so we arrive at the conclusion that psi k of R plus R1 is equal to e to the I k dot R1 times psi k of R, which if you may recall, is really the alternative form of Bloch's theorem, which is what we had just proven, right? This is equal to that. That's an alternative form of Bloch's theorem. We started off with our tight binding expression for our wave function, and we showed that that expression for the wave function satisfies Bloch's theorem. Okay, so good. Let's note a very important aspect here. Let us note that each atomic orbital results in a Bloch function. Right? In other words, if we have one atom per unit cell, and if we consider the 1s, 2s, 2px, 2py, 2pz orbitals, that's 5 orbitals, then we will have 5 Bloch functions, and the total wave function will be written as a linear combination of these 5 Bloch functions. So there it is, the words that I have just said are written down. So each atomic orbital results in a Bloch function. If we have one atom per unit cell, and if we consider a bunch of atomic orbitals per atom, we will have as many Bloch functions as the number of atomic orbitals considered. And in the end, our wave function psi k of r of our electron is in this periodic solid is going to be a linear combination of those Bloch functions. So we are going to illustrate all of this using a simple example. We are going to consider a 1D lattice of atoms, and we are going to consider one atom per unit cell, and one atomic orbital, the 1s atomic orbital per atom. And let us write down our Schrodinger's equation in simple form first, where our psi k, the wave function, is of course given by our tight binding prescription. So there it is. Xj, capital Xj is of course the location of our atoms. And let us also recall that our Hamiltonian will have two pieces, right? There is the kinetic energy operator and the potential energy. And of course, we have written down our del squared operator as d squared over dx squared, because that's what it is in 1D. And our potential V of x is of course a periodic quantity. And we had seen this picture before, this picture of periodic potential, and the lattice spacing of this periodic lattice is going to be assumed as A, which means xj is going to be equal to j times A, right? Where A is of course the lattice constant and j is some integer. So good, we got all the pieces in place, and what we are going to do now is we are going to go back to our Schrodinger's equation, which is h psi equals E psi, which we are going to call as equation 1, right? And then we're going to multiply that equation on the left on both sides with psi star of x and integrate over all of space. And when we do that, we will get the following steps. The first of which is simply this equation over here. Now let's take a look at the expression on the right hand side. It's got the energy E times an integral of psi star of x times psi of x integrated over all of space. So let us stick in our expression for psi k of x, which let us recall is very simply that. This is the equation at the very top of the screen. So what we are going to do is we are going to stick in this quantity over here and there, and that's just the complex conjugate of that. And then we're going to multiply the two. We're going to have two summations to deal with, and then we're going to perform the integration. So let's take a look at what happens when we handle the summations and do the integration. Okay, so we got a double sum, and we got our two phi's, and for simplicity I just dropped the 1s subscript, which I should really put just beneath our two small phi's. Okay, so we got a product of the two phi's, and bear in mind that this is xj and this is xj prime, right? So we have j and j prime, the summations over those two indices. Now, if we assume that the overlap between adjacent atomic orbitals is 0, our drastic simplification happens, right? So you bear in mind that these two are summations over all atom positions, and so this is really a product of two atomic orbitals, and the products could involve the same atom or adjacent atoms or atoms that are farther than adjacent atoms. What we are saying is that the overlap between even adjacent atoms is 0, which means all the terms of this double summation will vanish except when j equals j prime. Right, and so when that happens, our double sum becomes a single sum, and we get the following. And of course, we do know that the integral of the modulo square of our wave function of our atomic orbital has to equal 1, right? So you can take this summation outside, and so the integral of this modulo square of our atomic orbital over all of space has to be equal to 1, and of course the sum it goes from 1 to n, and so that sum of 1 is nothing but n, right? So this entire piece over here is n, so n divided by n will give us 1, and so this integral over here is equal to 1. Okay, now we have taken care of this piece. This piece is just 1. What about that piece? That's our next task. Let me give myself a little room. That's the integral we wish to evaluate, and it works out to be the following. Okay, so there it is. So all we have done is we started off with this integral, and we stuck in the expression for our wave function as prescribed within our tight binding situation, and we get this somewhat biggish looking expression. And this is actually a double summation. In order to save space, I just wrote down as a single summation, but I have two indices there, j and j prime, indicating that it is actually a double summation. And j and j prime are integers that vary, that can go from 1 to n. Okay, in order to simplify this whole expression further, we're going to make some assumptions, right? So we're going to say that this integral here is going to be non-zero only under two special cases. Either when j equals j prime, meaning we're talking about the same atom, right? Bear in mind that the j and j prime label atoms, right? So when j equals j prime, we are talking about the same atom. These two wave functions are located, clamped at the same position. So under those situations, this integral will not be 0. And the other situation is when j and j prime correspond to adjacent atoms, nearest neighbors, right? There are two possibilities. Either j is to the left of j prime, or atom j is to the right of j prime, right? So there are only three choices of j and j prime that this integral will be non-zero. Right, so there are going to be only three terms at the very end of the day. Okay, so let's write those three terms down. Okay, so there it is. Let us step through this carefully, right? So again, let me note that this is a double summation. So let us say we keep one of the summations, which is the j summation, intact, right? So you have 1 over n, and then one of the summations is kept intact. That's the summation over j. And now for each value of j, we need to evaluate the inner summation, which is the summation over j prime. So what we are saying is that j prime has to be either equal to j, or it has to be 1 less than j, or it has to be 1 more than j. Right? Those are the two. The last two situations correspond to atoms being adjacent to each other, right? So when j prime equals j, we are talking about the same atom, right? So when j prime equals j, this exponential goes to 0, and so e to the I k times 0 is just 1, and what will survive is phi of x minus xj times h times phi of x minus xj, again integrated over all of space. That is what we are calling as h naught. The second term which will survive is when j prime is 1 less than j. And remember that xj is nothing but j times a, right? Because xj is nothing but a real space lattice vector. So xj is equal to j times a, where a is the lattice constant. So when j prime is 1 less than j, xj minus xj prime is nothing but a. So the exponential here is e to the I k a. That's what we have here. And the integral corresponding to that situation is what we are calling as h1. Likewise, when j prime is 1 more than a, xj minus xj prime is minus a. And so this exponential becomes e to the minus ika. And the integral, if you think about it a little bit, will be exactly the same as the previous integral. So this is h1, just like this is h1. Okay, now we still have this first summation. What is going to happen to that? Bear in mind that this entire summand has no dependence on j, right? And so this summand is going to be the same thing for any value of j, for all values of j. Now j is going to run from 1 to n, and so when you sum this summand, which is independent of j, from 1 to n, you will essentially get this summand times n. So that n will cancel this n, and so we will be just left with the summand as this integral. So there you go. So our this entire expression has become just this simplified one, and you can pull out the h1 out of this piece over here, and you get e to the I k a plus e to the minus I k a, which is nothing but 2 times cosine k a, and so we get this as the final expression for this integral over there. Now, just for completeness, we are going to write down what h0 and h1 are. Bear in mind that h0 and h1 are nothing but some special choices of those integrals, right? So let's just write those down just for completeness. So those are our h0 and h1. Actually, we can get a little more sophisticated and make the observation that our Hamiltonian h can actually be split up into an atomic Hamiltonian and everything else, right? Remember that our Hamiltonian h is for our electron in a periodic arrangement of nuclei, periodic arrangement of atoms, right? So so which means that that Hamiltonian has as an atomic component and a component due to the potentials of all of the other atoms. So this particular integral over here can really be split up into two, and if we do that, one of them would be an atomic Hamiltonian, and of course the atomic wave function times the atomic Hamiltonian times the atomic wave function integrated over all of space will just give you the 1s energy level, and everything else that is left over is some constant, right? So one could do that. Okay, in any case, we have our simplified expression for our integral involving the Hamiltonian, and that is very simply this. So let us just step back a little bit and see what we have really accomplished so far, right? Let's go back all the way to here, right? So this was our original this was our original Schrodinger's equation that we wanted to solve, which is up here. We used the tight binding situation and defined our wave function for our system in this manner, and we knew that this was our Hamiltonian, and we took this wave function, stuck it into our Hamiltonian, multiplied that particular equation on the left by psi star and integrated over all of space, and we basically got this expression over here, right? we evaluated this integral to be 1, and which basically left us with this integral over here as E. Okay, now that particular integral has been evaluated to be this quantity over there, right? Which basically means that our E, our electronic energy, is this. Okay, let's write that down and let's make a plot of that. Let me make a little room for myself. Okay, so the top of the slide is the expression for electronic energy, which is equal to H naught plus 2H1 times cosine Ka. H naught and H1 are of course constants, and so if you plotted E as a function of K, you're going to get a periodic function, a cosine, right? And in fact, that's exactly what is plotted over here. And of course, it's plotted just within the first Bravon zone, right? Minus pi over a to plus pi over a. If you were to plot it for all values of K, what you would get is of course a cosine function which keeps oscillating like that on both sides, of course. But we have restricted our attention to just within the first Bravon zone. So the important point to note here is that our single 1s wave function, atomic orbital, our single 1s level of our isolated atom has become a band. This is our band. This is our 1s band, right? And of course, you can verify that the minimum over here, that energy is equal to H naught plus 2H1, and the maximum there is H naught minus 2H1. What will happen if A goes to infinity? This is something you can actually quite easily fathom. Let's go back. Oh yeah, there it is. Let's take a look at H1, right? What happens when A goes to infinity? When A goes to infinity, it basically means that this wave function, this atomic orbital, is going to be very, very far with respect to this one. It's so far away that this integral is going to vanish. It's going to be 0 because this wave function is not going to overlap with that too much. And so this integral will just go to 0. So H1 will go to 0, and so E will just be equal to H naught for all values of K, right? So there is no dispersion. So we are encountering an expression that we have seen before, and that is dispersion. Dispersion is essentially the variation of the energy with respect to K. So if A goes to infinity, there is going to be no dispersion, meaning it is going to have a flat line at E equals H naught. That's going to be very close, or in fact equal to the atomic 1s energy level. So when A goes to 0, you have a bunch of isolated atoms, and their energy, the electronic energy, is going to be just the 1s level. When you bring these atoms close together, the atomic orbitals start interacting and overlapping, etc., etc., and because of the periodic potential that you have set up, now your bunch of your infinite number of 1s levels from the infinite number of atoms that you have brought together are going to come together and form a band, and that is what you're seeing over here. Now you can of course extend the argument further and ask what will happen if you had originally considered the 2s and the 2p orbitals in addition to the 1s level. When you do that, you get additional bands. How are those bands going to look? So there it is. Here is a new band. I've just of course exaggerated the band gap and so forth, but the point is that you will have another band if you introduce another level, let's say the p level. So then that would be the p band. So we got the S band and the P band. Why do we say that? This is something we had actually encountered towards the very end of the previous lecture. We can actually visualize how the wave function would look at special points, such as here at the zone boundary over there, over here, over there, and so forth. And you would actually see that those wave functions look S-like and P-like. In fact, bonding S-like, anti-bonding S-like, bonding P-like, anti-bonding P-like. And it will be very nicely correlated with the wave function pictures that I drew at the very end of the previous lecture. Let's very quickly take a look at how the wave functions are going to look at these special k point values. Okay, so here are some pictorial depictions of how our wave functions would look like. At the lowest energy value over there, we will have our s atomic orbitals arranged in a bonding fashion through and through. This is something we had encountered in the past couple of times. Recall our discussion of lithium, the lithium N system, right? So at that point we have s orbitals arranged in a bonding fashion, and over here at the top part of that band we have our s orbitals but arranged in an anti-bonding fashion through and through. Between any two atoms you have a node, and that is because this is a positive wave function, this is negative, and so there has to be a node in between. Likewise, this is negative, that is positive, there has to be a node in between, and so forth. So it's anti-bonding combination through and through, right? And of course, at intermediate values of these energies, the wave function that would correspond to would have intermediate number of nodes. Now, switching to this this energy level over here, the bottom of the next band is going to be depicted using p-type orbitals, right? So you got a bunch of p orbitals, 4 p orbitals in this depiction, and of course each p orbital will have a positive and a negative lobe, and if the different p orbitals are arranged in such a manner that a negative lobe is close to a negative lobe from the next atom, and a positive lobe is close to a positive lobe from the adjacent atom, you got bonding combinations through and through of the p orbital. So that's our bonding p combination. And likewise, at the very top of that band, you got again p orbitals but arranged in a anti-bonding combination through and through. You see negative lobe hitting against a positive lobe, and same thing everywhere. So it's an anti-bonding combination through and through. Now, we did encounter a band structure plot like this in the previous lecture when we discussed the nearly free electron model, and if you recall, the wave functions were drawn a little bit differently in that case, and but those wave functions can actually be correlated with the ones that I just have drawn over here. And here are the wave function depictions within the nearly free electron model, right? So NFE for nearly free electron, and TB for tight binding. This is the tight binding picture of the wave functions, and this is the nearly free electron picture of the wave functions. These are the wave functions that I drew at the very end of the previous lecture. Although I should admit that there was a slight error in, I think, the top wave function that I drew in the previous lecture. But in any case, you can see that there is close correspondence between these pictures and these pictures. For example, let's take a look at our bonding combination of the s orbitals. This is shown in the tight binding picture in this manner. In the nearly free electron model shown in that manner, you can see that these are bonding combinations through and through. And next, let's go on to this picture over here, the anti-bonding combination of the s orbitals, plus minus and so forth. Likewise, you got plus minus and so forth. And going now to the bonding combination of the p, you will see that there is a positive lobe here, negative here, and a negative in the adjacent atom, and which means you got the negative regions of the wave function in this part over here. You got the negative region over there, and then positive, negative, and so forth, which will correlate very well with what you see in this entire wave function picture. Likewise, this is the anti-bonding combination of the p orbitals, and you can verify by inspection that this picture correlates to the behavior of this picture of the wave function. So you see the tight binding and the nearly free electron models lead us to the same results at the very end qualitatively. The wave function pictures of the tight binding model match up with the wave function picture of the nearly free electron model, and likewise the band structure plot that we get at the end is essentially the same as what we got using the nearly free electron model. Although we started at two extreme situations, we make the right approximations and we arrive at the same conclusions in the end, that we get bands and we get band gaps at special regions of the Bravon zone and so forth. So this concludes today's lecture, and what we are going to do next is to look at actual calculations of energy band structures and actual band structures of various important materials and so forth. Thank you.